In this video, I'll describe how to apply limits to compute the instantaneous rates of change. Here are the main points that we'll be addressing in the video. Please read these and think about them carefully as you watch the video. In addition to defining the derivative of a function f at x equals a, the limit definition of derivative, limit as delta x approaches 0, of f of a plus delta x minus f of a over delta x, can be used to calculate the instantaneous rate of change of f of x with respect to x at a specific value of x. Using the limit definition of derivative to compute instantaneous rates of change requires algebraically manipulating the difference quotient to cancel the delta x in the denominator so that the limit can be easily evaluated. Multiplying the numerator and denominator of the difference quotient by the conjugate of the numerator is a potentially useful strategy for algebraically manipulating the difference quotient to compute the instantaneous rates of change of a square root functions. Here is a square. If x is the area of the square, what is the rate of change of the side length with respect to the square's area when the area is 5 square centimeter? Initially, it seems like we don't need to use a variable because we already know the area of the square. But if we're interested in thinking about the rate of change, then we need to imagine that the square is growing, so that the side length and the area are both getting larger. And right when the area is 5, we want to know the rate of change of the side length. So for our original square, we'll let f of x represent the square side length. Then f of x equal to the square root of x, since the square root of x times the square root of x is x, the square's area. So essentially, our task is to determine the instantaneous rate of change of f of x with respect to x when x equals 5. The first step in doing this is to represent the average rate of change of the square side length with respect to its area. Right now, the area of the square is 5 square centimeters. So the length of each side is the square root of 5 centimeters, which we can write as f of 5. Now imagine the square's area increasing by delta x square centimeters. Then the length of the side of this larger blue square will be f of 5 plus delta x centimeters. So the average rate of change of the square side length with respect to its area is given by the change in the square side length. So f of 5 plus delta x minus f of 5 divided by the corresponding change in square's area. To get the instantaneous rate of change of the square side length with respect to its area when the area is 5 square centimeters, we'll use the limiting value of this average rate of change as the change in square area approaches 0. Since we know a formula for function f, we can replace f of 5 plus delta x with the square root and f of 5 with square root. Now, let's try to evaluate this limit to determine a numerical value for the instantaneous rate of change. Your first instinct might be to copy this expression and then break apart square root of sum of 5 and delta x. But this is not valid algebraic expression. So we need to try something else. Another attempt might be to copy the expression and then try plugging in 0 for delta x. In the first square root, this just leaves you with 5. And the numerator just becomes 0. And the denominator is also 0. So this leaves us with an indeterminate form, which cannot be evaluated. So we need a different technique for evaluating this limit. The challenge with evaluating this limit is dealing with the square root expression. After we copy the expression, a strategy for accomplishing this is to multiply the numerator and the denominator of this expression by something called the conjugate of the numerator. In this case, the conjugate of the numerator is the square root of 5 plus delta x plus the square root of 5. What makes its conjugate is that we're adding root 5 instead of subtracting it. Of course, if we just multiply the numerator by its conjugate, then we're changing the fraction. But if we also multiply the denominator by conjugate, then we're really multiplying by something that is equivalent to 1. So it won't change the fraction. Let's give ourselves some room to actually multiply this fraction. When we multiply the first term to the numerator, we're multiplying a square root by itself. So this is equivalent to just 5 plus delta x. When we multiply the first term to the second fraction, in the first fraction with the second term, the second fraction, we're multiplying root 5 times root 5 plus delta x. There isn't a way to simplify this, so we just add it below. When we multiply the second term in the first fraction with the first term in the second fraction, we have got the same thing as before, except this time we're subtracting the term. When we multiply the second terms, we have negative root 5 times root 5, which is equal to negative 5. And we'll include this in the below. Finally, we multiply the denominators. We can't simplify this, so we'll just write this in the denominator below. Now let's see if there's some terms that cancel. Positive 5 and negative 5 add to 0. So they'll cancel. We can remove them from the fraction. Also, the two middle terms in the numerator are additive inverses of each other. So they add to 0 and cancel. So we can remove them from the fraction. Now, both numerator and denominator of the fraction have a delta x term, which we can factor out, which leaves us with a 1 in the numerator. This new fraction is equivalent to 1, so we can remove it from the product. Let's make this a little more compact. In this limit, delta x is getting closer to 0. So the limiting value of this expression as delta x approaches 0 is 1 divided by square root of 5 plus square root of 5. Or simply 1 over 2 root 5. To summarize what we just did, we started with a square whose side lengths were growing. We were trying to compute the rate of change of the square's side length with respect to its area when the area is 5 square centimeters. We used the function f to denote the relationship between square's area and side length. So we were trying to compute the derivative of f when x was equal to 5 centimeters. We used the definition of the derivative to write this as a limit and this some algebraic computation to evaluate this limit as equal to 1 over 2 root 5. So the value of the instantaneous rate change is 1 over 2 root 5 centimeter per square centimeter. And this is an example of more general process. To use a limit definition to compute the values of derivatives, you start with a function. In our example, it was a square root of x, but it could be anything, any other functions. Then if you want to compute the value of derivative of f at x equals a, you write the average rate change of as x increases by an amount of delta x, and then look at the limiting value as delta x approaches 0. Then you plug up plus delta x and a into the formula. Next, you do some algebra to try to isolate the delta x, and finally compute the limiting value as delta x opens to 0.